this question is not one of these inverse square law questions. It's asking how far apart are they. So this one you just have to solve for the distance. So I'm going to go ahead and write my stuff out here. I'm going to start up here to make sure I have room. It says two charges of 1.6 times 10 to the negative 19, negative 1.6. Now it only says the number once. Oh, I didn't say the unit, coulombs. Wow. But it does say two charges, so you got to read it. Be careful. So Q1 then would be negative 1.6 times 10 to the negative 19, and so would Q2. There's two charges with that charge. And they're coulombs, even though it doesn't say. Experience a force of 5 newtons. That's a force. 5 newtons. How far apart are they? Asking for the distance. We've got our formula right there. I'm going to write my stuff out down here. I got 5 newtons equals K. That K is, can I use this? No, I can't. I already wrote it over there. That K, it'll be given to you every time. You don't have to remember it, but it's 8.99 times 10 to the 9. So I'll plug it in right here. 8.99 times 10 to the 9. Q1 is at negative 1.6 times 10 to the negative 19, and so is Q2. The reason we're seeing these numbers, that negative 1.6 times 10 to the negative 19, a lot is because that is the charge on an electron. So I could have said 2 electrons of that charge. That's the charge on an electron. Anyway, I'm glad we're using familiar numbers because I remember what that is. We're looking for d squared, but let's simplify first. I guess I got out here. 5 newtons equals, when you multiply all these, you get 2.3 times 10 to the negative 28 over d squared. To continue to solve this, we need to get that out of there. Whenever you're looking for something in the denominator, that makes it difficult. Get it out of there. It says divided by d squared, so we'll multiply by d squared. Those cancel, so now we've got 5 newtons times d squared equals that 2.3 times 10 to the negative 28. From here, we need to divide both sides by 5 because it says d squared times 5, and we wanted to say d squared equals and then d equals. So let's see, those cancel. I divide those by 5. Whatever you get there, you put it down there and then square root it, you'll get the answer. But I just wanted to show you the process here because I know some people have trouble remembering when it's in the denominator. That's the hardest part of this algebra stuff that we do, in my opinion. It's when something's in the denominator. Anyway, today's thing is we're going to use some organizational tools to help us solve some of this stuff here. All right. When we do these are the two questions that are new that you'll be given today. We'll be calculating total current and total resistance and total voltage, and we'll be using V equals IR, and we've done all those things before. And that's all these tables are, but these tables are more of a, once you get the whole thing filled out, that's all there is for this circuit. Like, you can't figure out anything else for it in terms of voltage, current, and resistance. So we'll be getting the voltage, the current, and the resistance on each of these places. So that's what that means. Circuit position 1, the resistance is 10. That means that R1 here is 10 ohms, and R2 here is 20 ohms, and R3 here is 30 ohms. Because that's what R2 is, that's what R3 is. Oh, it also tells us the voltage. The total voltage is 6, which means that this battery over here is 6. And the only reason that we can already know that that battery is 6 from the total voltage is because there's only one battery. So if the total voltage is 6, that one's the one that's got to be 6. So there's a certain order to do this in. So I'll show you where to start on this table. You always do this box first. So, well, you do the box first where you can find the total. So in these cases, it'll always give you all the resistances. So you'll find that total first, and then you'll find this box next. But if it gave you all the voltages first and didn't give you the total voltage, first you'd find the total voltage, and then so what we'll do is we'll find this one here. Now you've got to look at the rules. I posted the rules on the assignment, so you should be able to look at them. The rules for series, I'll show you what rules I'm talking about. There. I'm talking about these rules. Can't see if y'all can see that or not, but the rules there at the top where it says for series, our total is R1 plus R2 plus R3, and for parallel, our total is 1 over R1 plus 1 over R2. So you'll do that box first. This is a series circuit, so total resistance is calculated by just adding them up. So you'll add these up, 10 plus 20 plus 30, put that right there. After that, use V equals IR by plugging in 6 for V and that total for R, and then solve for I, like this. You'll have 6 for V, and you'll solve for I, and you'll have whatever you get right there for R. After you get a number right here, so we did this second, I'll put a little number there, just to know that we did it. That's when, go back and look at your rules, figure out what kind of circuit this is again. Okay, it's a series circuit, look under series circuit. Find the one that says, the little rule that says something's the same anywhere in that type of circuit. So if you're doing a series circuit, it says current is the same anywhere in a series circuit. If you're doing a parallel circuit, it says voltage is the same anywhere in a parallel circuit. So like on this one, we could go ahead and say, okay, it's a parallel circuit, voltage, all of these would be, each of these would be 6 volts. This is a series one, so we'll take whatever number we got there, whatever number the total was, and each of these boxes will be the same as the total. And after you get all these, so these boxes will all be the same number as that one because this is a series circuit, and series is the same anywhere in a series circuit. Then you use V equals IR again to fill out these. V equals IR, V equals I times R. So you would just do this number times 10 and put that there, and then this number times 20 and put that there, etc. I'm going to do the optional question that's at the end because it's a little much. So if that doesn't sound like something that interests you, y'all can stop watching and start the assignment. But I'm going to show you this one anyway, and I'll actually do the whole problem this time. Just frozen? Okay. Now, there we go. If you feel like y'all got this, y'all can start. If you want to wait for me to do this, that's fine too, but it's going to take a while and I don't want you to run out of time. So, we're still going to do this the same order, this box first and this box second, because we'll find the total of what we can. So this is the one we can find the total for, and then we'll use V equals IR to find this one. So we'll go ahead and find this total. Now, I can't do it just one way because this circuit is all mixed up. It's a series circuit, but a section of it is in parallel. So this R1 is in parallel with this whole group of R2 and R3. So let's label my stuff over here. All right, 10 and 20 and 30. For series, the total resistance is R1 plus R2 plus R3. If we're looking at this circuit as this resistor is in parallel with this group of resistors, then we'll say the total resistance is R1 plus this whole thing would be R2. So if we find the total resistance for this whole thing, then we can say, okay, 10 plus that total resistance would be the total resistance altogether. So let's find this total resistance first. These two are in parallel with each other. So we'll use the total resistance weird formula with 1 over R1 plus 1 over R2. The way I like to do it is to find the least common multiple for these fractions so that we can get them to add. So let's see. that would be 60, right? 1/20th is equal to 3/60ths, and 1/30th is equal to 2/60ths, and that whole thing is equal to 5/60ths, which is equal to, because dividing by a fraction is the same as multiplying by its reciprocal, 1 divided by 5/60 is the same as multiplying by, is 1 multiplied by 60 divided by 5. And that's the same as 1 times 12, so the total resistance for that group of R2 and R3 is 12. And now we can add up the ones regular. So now this 10 is in series with this group, the total resistance of which is 12. So we've got 10 plus 12, and that makes this total resistance 22. Now we can use V equals IR to find this other box. And I'm going to color code it here again. Second. V equals IR. We're just plugging in 6 volts from the total here. We're looking for I for that one. And we've got R, 22 ohms. To solve for I, it says I times 22, so I'll make that cancel by dividing by 22. And I get 0.27. 0.27 amps is I, so here we go. 0.27. All right, the next step is to find the one that's the same the whole way. If it's a parallel circuit, voltage is the same the whole way, so we put 6. And if it's a series circuit, current's the same the whole way, so we put 0.27 in each box. But it's neither. It's got a parallel section inside a series circuit. But because this circuit's primarily a series circuit, I'm going to say that if the total current is 0.27, that the current across R1, that since R1 is in series before it gets to all this, is the current across R1 would be 0.27 also. Because if current's the same anywhere in a series circuit, if it's 0.27 here, it'll be 0.27 here, and this total will be 0.27. So I can't write down, 0.27 for both of these or anything, so I'll just write it for R1. What am I doing? 0.27 amps. There. Well, the next step I can do is I can say, I can do this one with V equals IR, 0.27 times 10. So let's do that over here. Using V equals IR again, looking for V. I is 0.27, and R is 10 ohms. I guess that's amps, okay. And 0.27 times 10 would be 2.72. I'm writing this little bar here because these are irrational numbers. They're, in the calculator, this was 0.2727272727 forever. And that's what this means. This is 2.727272 forever. All right. This is where it gets a little more difficult because there's not a clear way forward. This is why I'm doing this question. The rest of them are easy. This one's difficult because it's all mixed up. But, okay, if R1 has 2.72 volts on it, that means that the rest of the voltage is going over here. But this one used up 2.72, so the rest of the 6 volts is the total voltage for this area. So if I can find the total for that parallel, we can get something done. So that's what I'm going to do. If they had the total voltage for the whole circuit was 6 volts and the voltage for that one component was 2.72, because of the formula for so the formula for total voltage in a series circuit is total voltage is V1 plus V2 plus V3, etc. in this case, in our series circuit, we've got V1 here, and we're acting like this whole thing is V2. This section of parallel is V2. So we're finding the total voltage for that section of parallel, that'll be V2. So if we say, okay, the total voltage is the voltage of V1 plus the voltage of V2, we can figure out the voltage of V2 if we subtract. And 2.72 minus 2.72 is 0, so those cancel. And whatever we get will be V2, which is just the total over there. We won't be able to write that down because there's two different boxes there, but let's see. So what I get, if I do that, is 3.27. All right. Now that we know the total voltage for parallel, let's go look at the rules for parallel. And it turns out they're going to help us out because it says voltage is the same anywhere in a parallel circuit. So if the total is 3.27, that means that these other boxes will be 3.27. So here we go. 3.27 volts. 3.27 volts. Cool. The only thing left to do is to use V equals IR to figure out these other boxes. And I did that in my calculator earlier. I got 0.1636. And the 36 is repeating after that, but I'm not sure if that's accurate to express it that way, so I'm not going to do that. And the 90 here is also repeating. And I got my table filled out. Now, we should be able to check this because, so I'm going to do a little check here to make sure I did it right. Because the total current, this whole thing is a series circuit. But this is a parallel section. So the parallel rules for current say that total voltage is I1 plus I2. So it would be the voltage on this one plus the voltage on this one is the total. And if we calculate the total of 0.1636 plus 0.1090, those two currents that I got, you get 0.27. And that makes sense because the whole thing's a series circuit and current's the same anywhere in a series circuit. It should be 0.27 here, and this total should be 0.27, and that's what we got. This plus this is 0.27, so the total current in that parallel section is 0.27. That's why this isn't a required question, because it's a lot. I'll leave it up here in case it helps. You all are welcome to try this question if you have time and want to. Yes. Thanks for your patience with the video here. I think they can still hear me. Just stop buttons. It's going to be a 2 GB video. Oh, I'm pressing the stop button now.